Potentiometer is an electric circuit that's used to measure small amounts of EMF. What it consists of is a primary circuit such as this, which consists of a cell, a variable resistor. Sometimes this variable resistor may not exist. Sometimes it could be, instead of a variable resistor, that could just be an internal resistance of the cell. There is also usually a wire, a straight wire that's mounted on the meter rule. So the resistance of the section of wire that we'll use is proportional to the length of the wire. So we're going to read off the length of the wire using the meter rule. So let's just clean the meter rule off. Very often the potentiometer is not drawn with the meter rule. So the wire is just represented by a single straight line. Let's call one end of the wire A and the other end B. Now, if you remember the potential divider rule, the potential difference across any 2 points along this wire is going to be a fraction of the EMF E1. Let's say we are talking about these two positions. Let's call this AJ. The potential difference across AJ will be the fraction of the resistance of AJ to that of the total resistance in this primary circuit, which is AB, the resistance of AB plus the variable resistor that we have here. Of course, if the battery has an internal resistance, then we need to include the internal resistance in here. This ratio multiplied by the EMF E1 will give you the potential difference across AJ. We are going to attach an EMF or a device for which we're trying to measure its potential difference across AJ, and J can be any position along this meter rule. The simplest case is where we have another cell that's attached to AJ. J is basically the point in contact between the jockey, this will be a jockey, and the meter rule, and J, the point of contact, can be shifted anywhere along this meter rule. When this jockey is shifted, what we'll look out for is for the galvanometer over here to register a null deflection. That's to say that there's no current flowing through this galvanometer. When that happens, the potential difference across these 2 points here will be equal to the potential difference across AJ. Why is that so? Well, if you look at this part here, this is just a single wire, so there's no reason why there should be any potential difference, because the wire should have negligible resistance. And when a null deflection is obtained, that means that the potential J is equal to the potential at this end of the terminal of this cell, which therefore would suggest that the potential difference across this cell and AJ will be the same. Let's call the EMF of this cell E2. In order to measure E2 equals to the potential difference across AJ, which is the fraction of the resistance of AJ to the total resistance within the primary circuit multiplied by E1, which is the EMF of the primary circuit. The secondary circuit over here could be anything. It may be just a single cell. There might be a resistor in series with it. But in this case, do note, however, that because there is no current flow, the potential difference that AJ measures is still equal to E2. However, if we're going to connect another resistor in parallel to E2, the potential difference across AJ is now not going to be equal to E2. Instead, it will be the potential difference across the external resistor over here. So usually what we do is we form an equation with the potential difference across AJ on the right and the potential difference across what we're trying to measure on the left. This is the potential difference across AJ. We're going to equate it to the potential difference that we're trying to measure here. In this case, let's call this R1. Small r is the internal resistance of the second cell, the secondary cell. So the potential difference that AJ is going to measure is the terminal potential difference across E2, or rather the potential difference across R1. That can be determined by taking the ratio of R1 to the total resistance within the secondary circuit multiplied by E2. Once we've got this right, this basic right, we can change the secondary circuit into anything. As long as we're able to apply the potential divider rule, we should be able to form an equation equating the potential difference that we're trying to measure to the potential difference across AT.